The Shandong Taishan Group produces approximately 4 million metric tons of low-carbon steel and 1 million metric tons of stainless steel annually, with its hot wide strip production centered on a Steckel mill. The SMS Group partnered with Shandong Taishan for an extensive revamp of the production line, aiming to enhance both output and quality. The upgraded line consists of a descaler, roughing mill with edger, crop shear, Steckel rolling mill, laminar cooling system, and coiler. SMS's modernization plan included relocating equipment, adding a second coiler, and installing a new 3-stand finishing mill. The revamp was completed in 2 phases, significantly reducing foundation work and cutting down on downtime by 37 days. Central to SMS's work were advanced electrical and automation systems, featuring Level 1 and Level 2 controls, new converters, and reinforced laminar cooling. These systems were rigorously tested in China and Germany for seamless integration. Additionally, operators received training in the new ergonomic interfaces and rolling technology, ensuring efficient system operation. With improved automation, Shandong Taishan's line can produce higher-grade steel with better strip geometry, thickness tolerance, and higher cooling rates. This revamp has positioned the company to achieve its goals, with SMS technology enabling future competitiveness and a reputation for quality steel production. The production starts with slabs, which are reheated in a high-tech digital furnace. These slabs are then processed through a traversing rolling mill, designed to create fine-grained properties in the steel, enhancing its strength and durability. Plates are rolled to precise dimensions according to customer specifications. Thermomechanical control, along with accelerated direct cooling and direct quenching, further improves abrasion resistance, toughness, and tensile strength, qualities essential for high-performance steel plates. SR Steel uses 3 primary steelmaking technologies: blast furnace, Corix, and direct reduced iron. Dry. This flexibility allows the use of various raw materials and energy sources, enhancing efficiency and sustainability. The plate mill also incorporates advanced heat treatment facilities that offer austenitizing, normalizing, quenching, and tempering, producing steel with ideal mechanical properties. Ultrasonic testing and precise cutting equipment ensure each plate meets stringent international quality standards. SR Steel's plates serve multiple industries: structural steel for petrochemical, oil, and wind energy sectors, pressure vessel steel for nuclear and chemical processing, wear-resistant steel for mining and defense, and marine-grade steel for shipbuilding. Located in Hazira on India's west coast, SR Steel Complex benefits from comprehensive infrastructure, including port, road, and rail access, supporting the facility's role as a cornerstone of India's steel industry. 1. Split cutting of the raw material. The process begins with cutting the raw steel into segments, sized precisely according to the knife's specifications. Quality is critical here. Many top-tier knives use high-carbon, corrosion-resistant steel alloys like chrome molybdenum vanadium or Japanese Damascus steel. This carefully selected raw material ensures a robust, sharp blade capable of withstanding wear and tear over time. 2. Forging the knife blank. The raw steel piece is heated to over 1,000 degrees Celsius, becoming red-hot and malleable. At this stage, it is forged into a rough knife shape using a powerful drop hammer. Forging the knife under high pressure imparts strength to the steel structure, making it resilient and capable of holding a fine edge. 3. Deburring and cutting out the knife. Once the rough knife shape is forged, any excess material or irregularities are trimmed away in the deburring stage. Skilled artisans then refine the blank's shape, ensuring the knife has a clean and balanced profile. 4. Perforation. If the knife design includes riveted handles, holes are perforated into the tang, the part of the knife that extends into the handle. This allows for securely attaching the handle materials in later stages, contributing to both durability and ergonomic comfort. 5. Hardening processes. The knife blank undergoes several hardening stages, which are integral to achieving the desired strength and flexibility. Heating the knife blank. The blank is reheated to prepare it for rapid cooling, a technique that refines the steel's crystalline structure. Oil hardening. The hot blade is plunged into an oil bath, which cools it quickly, enhancing its hardness and making it resistant to corrosion. This rapid quenching is essential for maintaining edge sharpness and overall durability. Ice hardening. In some cases, the blade undergoes cryogenic treatment, being cooled to extremely low temperatures around -80 degrees Celsius. This process further hardens the steel, optimizing its molecular structure and reducing internal stresses, which enhances both resilience and edge retention. Six, straightening the knife blank. Once hardened, the knife blank is straightened to eliminate any minor warping that may have occurred during heating and cooling. Precision in this step is crucial, as any remaining irregularities could impact the knife's cutting performance and handling. 7. Grinding the blade. Grinding is a multi-phase process that shapes the cutting edge and reduces the blade to its final thickness. Grinding requires expert control to ensure the blade doesn't overheat, which could compromise the hardening process. This stage defines the blade's profile and thickness. 8. Grinding the back. The back or spine of the knife is ground to smooth out any rough edges and achieve a consistent thickness. This step also enhances the aesthetic quality and ergonomics of the knife. 9. Drying. After grinding, the blade is thoroughly dried to prevent any moisture from causing corrosion. Moisture at this stage could also interfere with subsequent processes, so complete drying is necessary. 10. Pre-grinding the bolster. The bolster, which serves as a bridge between the blade and handle, undergoes initial grinding to achieve a smooth transition. This enhances the balance and feel of the knife, which is particularly important for precision tasks and culinary applications. 11. Pleiston, fine grinding the blade. The fine grinding or Pleiston stage gives the blade its final polished edge. Fine abrasives are used to produce a smooth, mirror-like finish on the blade, which not only looks attractive but also aids in corrosion resistance and edge retention. 12. Cleaning. The blade is carefully cleaned to remove any grinding residues. Ultrasonic cleaning is often used to ensure even the tiniest particles are removed, leaving the blade spotless and ready for the handle assembly. 13. Ride-in, assembling the handles. Handles, whether wood or composite, are attached to the tang by hand. Each handle is riveted securely, creating a tight fit without gaps that could harbor bacteria. This attention to hygiene and ergonomics is a hallmark of high-quality knife production. 14. Osmahan, finishing the handles by hand. Skilled artisans polish the handle until it is smooth, comfortable, and sits securely in hand. This hand finishing stage is an art in itself, ensuring each knife feels balanced and easy to control. 15. Cleaning and in-process inspection. After assembly, the knife undergoes another thorough cleaning, followed by an inspection. Each knife is examined for straightness, smoothness, and quality of finish, as well as any potential defects that might affect performance. 16. Absian, sharpening the cutting edge on a grinding stone. The cutting edge is hand-sharpened on a grinding stone to achieve an ideal angle, often around 30 to 35 degrees depending on the knife's purpose. This angle is crucial for maintaining a keen, durable edge. Skilled craftsmen use laser measuring tools to verify the angle's precision. 17. Cutting inspection. Each knife is tested to ensure it performs to specification. A well-sharpened knife should slice effortlessly and maintain a consistent edge. Inspectors look for smooth, uniform cuts and any signs of blade deformation or dullness. 18. Axes are forged with enduring craftsmanship at Hultsbruk in Östergötland, Sweden, where smiths practice techniques dating back to 1697. This rare skill involves striking Swedish steel multiple times to shape the axe head, significantly enhancing its density, durability, and lifespan, qualities unmatched by simpler forging methods. A precise hardening process creates a resilient hard zone on the edge, allowing for sharpening without sacrificing strength. Each axe, whether for felling, splitting, or outdoor use, is crafted to meet specific demands and is built to last generations when properly cared for. The production process of rail steel shovels is a specialized procedure that optimizes strength, durability, and functionality. These shovels are crafted from high-quality railway rails, chosen for their high carbon content. This high-carbon rail steel provides exceptional strength while keeping the shovels lightweight, meeting the unique needs of demanding applications. A distinctive feature of these shovels is the high-tech double hardening process they undergo, which sets them apart from standard shovels. Double hardening is a specialized heat treatment that minimizes the reduction of volatile carbon during heating, preserving nearly all of the carbon content. The result is a steel with enhanced strength, improved elasticity, and greater wear resistance. This innovative hardening process provides the steel with resilience under intense use and resistance to deformation or breakage over time. To protect against corrosion, the shovel blade is coated with a high-strength varnish, ensuring longevity even in harsh environments. The shovels are also designed with user comfort in mind. The blade includes an ergonomic ledge for the foot, strategically shaped to fit the natural contours of the foot. This ledge not only enhances comfort but also serves as a structural reinforcement as it merges into the sleeve of the shovel, adding additional stability. The shovel sleeve is engineered with a unique unwelded seam, which serves an essential purpose. Unlike welded seams, this unwelded design ensures that the sleeve securely grips the handle even when exposed to changes in humidity, which can cause wood handles to expand or contract. This mechanism relies on the spring properties of steel, which allow the sleeve to adapt to pressure changes without generating excessive resistance. As a result, the junction between the handle and blade remains intact, and the shovel can withstand prolonged use without loosening or breaking. Another notable aspect is the self-sharpening edge of the shovel blade. Each shovel is initially sharpened, allowing it to be used for multiple purposes beyond digging, such as cutting through materials like wood, ice, and softer metals. This self-sharpening feature ensures the shovel remains effective for a variety of tasks over time, requiring minimal maintenance. Each shovel also comes with a logo for brand recognition and traceability, and a certificate of quality compliance according to international standards. This certification provides customers with assurance of the shovel's quality and durability. Furthermore, the shovel line includes a wide range of products to suit various needs, from digging and scooping to large and small household shovels. One, raw material preparation. 3CR13 stainless steel serves as the primary material. This high-quality steel, known for its corrosion resistance and toughness, is an excellent choice for kitchen knives. 2. Furnace preparation. The forge is loaded with premium carbon to achieve intense and even heat. The controlled burning of this carbon creates a high-temperature environment, crucial for manipulating the steel during the following stages. 3. Initial steel forging. Once the steel reaches the desired temperature in the furnace, it undergoes a physical-chemical reaction as it interacts with oxygen. This step removes impurities, enhancing the steel's purity and quality. The first round of forging begins, involving over 100 strikes with a pneumatic hammer, which compresses the steel, increasing its density and refining its molecular structure. This densification strengthens the metal and prepares it for further processing. 4. Refined iron forging. A separate iron component, which will later be combined with the 3CR13 steel, is also heated and forged. The iron is continuously adjusted within the furnace to ensure uniform heating, repeated over 15 times, to remove any residual impurities. This process typically lasts 20 minutes and aims to make the iron structurally dense, pure, and ready to merge with the steel. 5. Iron shaping and steel insertion. The heated iron is hammered into a rectangular block, and a long opening is created along its center. This slot is then filled with a pre-shaped steel bar that fits precisely, and the combined structure undergoes further forging. The composite material is repeatedly adjusted within the furnace to achieve even heating, enhancing its durability and facilitating the fusion of iron and steel. 6. Clay coating and intensive forging. The composite block, heated to the point where sparks fly, is removed from the furnace and coated in yellow clay from the Longchen Mountains. This clay layer ensures a uniform, pure edge and adds unique characteristics to the knife's final finish. With this coating, the steel-iron compound undergoes 180 more strikes, embedding the clay particles into the steel surface to protect the knife from brittleness and improve longevity. 7. Shaping and forging the blank. The glowing blank is forged into a rough rectangular shape with varying thicknesses. This step involves over 100 strikes to create a firm structure, preparing the knife for shaping. 8. Blade and handle shaping. Once the blank cools, it's reheated, and specific sizes and shapes are cut out for the blade and handle. The blade and handle are forged as a single piece, ensuring a durable bond that enhances the knife's balance and stability. 9. Heat treatment and tempering. The blade undergoes a 6-hour heat retention treatment to strengthen its structure, followed by quenching a sudden plunge into water to harden the blade. A final tempering step in the furnace restores flexibility and prevents brittleness. 10. Finishing touches. The knife's edge and surface are ground smooth, removing roughness. 6 stages of polishing, from coarse to fine, produce a mirror-like finish. The blade edge is then ground using a water-cooled whetstone, a critical step to preserve the steel's hardness and ensure a razor-sharp finish. This meticulous forging process results in a high-quality kitchen knife, rich in tradition and suited to last for generations, embodying Chinese craftsmanship at its finest. The aluminum tandem cold mill (TCM) for Chinalco Southwest Aluminium represents an advanced cold rolling system designed to process aluminum coils into thinner, more uniform sheets. The process begins with transporting aluminum coils from a hot rolling mill to a flat storage area, which has a capacity for 185 coils. From there, coils are moved to a high-rise storage system, featuring a large storage capacity of 748 compartments distributed along two aisles with stacking cranes. This high bay storage includes features like roof shutters, fans, and an internal and external air mixing area for efficient air circulation. Once the coils reach the cold rolling mill, they enter a double-base parallel cold mill tailored for producing lithographic tiles. The TCM is a two-stand mill with a strip width ranging between 800 and 1,800 millimeters, offering an annual production capacity of 200,000 tons. Equipped with a hot edge injection system, this TCM design helps manage strip temperature, essential for maintaining quality and consistency during rolling. The mill can produce thin aluminum sheets with a minimum exit thickness of 0.15 millimeters, meeting specifications for various applications that demand high precision. The interface between the high bay storage and the cold rolling mill area includes a pallet circulation system for smooth coil transportation, ensuring an efficient flow between storage and processing zones. Post-rolling, the coils move through a handling and inspection line, which includes an exit section with essential components such as a coil strapping machine, scale, and coil logistics system. This area ensures that all products are thoroughly checked and prepared for further processing or shipment. Chinalco's facility also prioritizes eco-friendly production. It employs an Air Wash Oil 300 system by SMS Group for exhaust gas cleaning, capturing and washing emissions to minimize environmental impact. Additionally, an oil-dish system is in place for removing hydraulic oil or grease, further ensuring that operations remain clean and sustainable. The aluminum coil production process begins with an aluminum slab, typically produced via continuous casting. These slabs, once homogenized, are prepared for hot rolling. First, the slab is heated in a reheating furnace to a temperature range of 500 to 600 degrees Celsius. This temperature softens the aluminum, improving its plasticity and making it suitable for rolling. After reheating, the slab undergoes pre-rolling or breakdown rolling in the roughing mill. Here, it is reduced to an intermediate thickness through a series of back-and-forth passes, often controlled by a hydraulic system to achieve uniform thickness. During these passes, both the top and bottom of the aluminum slab are rolled to maintain consistent mechanical properties and thickness distribution across the slab. Pre-rolling also helps eliminate any impurities or surface defects on the slab, ensuring a smooth surface for further reduction. The aluminum then moves to the finishing mill, where multiple stands, usually 4 to 6, apply consecutive reductions. This part of the process achieves the final coil thickness, typically between 2 and 10 millimeters, depending on the coil specifications. The finishing mill is highly automated, with rolling speeds up to 20 meters per second. Automated control systems monitor parameters such as temperature, rolling speed, thickness, and width, ensuring precise control over the final product's dimensional properties and surface quality. Once the desired thickness is achieved, the rolled aluminum strip is coiled while still warm. This warm coiling allows the aluminum to gradually cool, preventing thermal stresses that could lead to warping or other issues. The coil is then allowed to cool completely in controlled conditions to relieve any residual stresses. Finally, the coil undergoes a surface inspection and may be trimmed or cut to the required width. At this point, the coil is either ready for shipment or for further processing, such as cold rolling or surface treatment, to meet specific industry requirements. This process results in high-quality aluminum coils used in various applications, from automotive and aerospace to packaging and construction. The 12,000 cans per hour production line for 330 milliliters aluminum carbonated drinks is a highly automated process designed for efficiency, consistency, and quality control. The process begins with an automatic depalletizer, which receives palletized stacks of empty cans and transfers them onto a conveyor belt. This setup avoids manual handling and speeds up the flow of cans into the production line. From here, the cans are sent to an inline can washing machine to ensure cleanliness and remove any potential contaminants that may be present from storage or transportation. This washing machine typically uses high-pressure sprays to thoroughly clean the can interiors and exteriors. Once clean, the cans enter the high-power beverage mixing machine, where carbonated water, sweeteners, flavors, and other ingredients are combined precisely to create the drink formula. The mixing machine operates at high speed to maintain consistency across all cans and ensure carbonation levels are uniform. The next stage involves the automatic can filling and sealing 2-in-1 mono block. This equipment fills each can with the carbonated beverage and immediately seals it to maintain freshness and carbonation. The monoblock design streamlines the process, combining filling and sealing in one compact setup, and minimizes the chance of contamination. Post-sealing, cans are inspected for quality. The liquid level check machine confirms that each can is filled to the correct volume, rejecting any with underfills or overfills. The inside pressure inspector then checks that each can is pressurized to the proper level, crucial for carbonated beverages, ensuring they're shelf-stable and safe to consume. Finally, cans are packaged by the automatic shrink wrapping machine with a carton tray. This machine groups cans in desired quantities, wraps them with shrink film, and places them onto a carton tray ready for shipping. Crown Aerosols leads the aerosol packaging industry with cutting-edge technology and high-speed production processes that deliver diverse can heights and diameters. By leveraging advanced beacon technology and in-house component manufacturing, Crown ensures seamless, high-quality production. The company is a global leader in tinplate aerosol cans, combining unique decorating capabilities with the latest aerosol manufacturing techniques to meet strict industry standards. This commitment to excellence enables Crown to support global brands in standing out in competitive markets. Crown's packaging solutions cater to everyday consumer demands with durability, aesthetic appeal, and reliable functionality, helping brands meet the highest quality expectations. The Tension Sensing Center optimizes the alignment and tension of topreg during composite material processing. This system begins with the Z-plane roller, which carefully controls the topreg's alignment to ensure precision through every stage. Next, the delivery head carriage feeds the topreg forward while the alignment roller continuously checks and corrects the path, preventing drift. With all components set up, the topreg is then threaded through the delivery end to establish a steady, guided path. Once the threading is complete, a spiral wrap layer is applied around the material, followed by a ring layer. These layers reinforce the composite by providing structural stability and desired tension levels. Observing compaction of material A under the ring layer is essential as it verifies the uniformity and integrity of the layers. The final step involves applying a tension bandage, compressing the layers and securing them tightly. This compression enhances material cohesion, stability, and resilience, creating a durable composite. Each element of the tension sensing center works in unison to control alignment, layer application, and tension, yielding consistent, high-quality composite materials.